Hello, geometry students. Today we are looking at section 4.7 entitled Triangles and Coordinate Proof. A coordinate proof is a little different from other kinds of proof because you are operating in a coordinate plane, and now you're going to see why we reviewed slopes and equations for lines and intercepts and so on. So in order to give you a sense of how this section works, I'm going to tackle a problem here. It's example 6 on page 246, but it's not actually fully worked out in your book. So I'm going to show you how we do this. We have a figure here, and it starts out, it is OTUV. Point O is at 0, 0, the origin. Point T is at M, comma, K. That means we don't know the numerical values. We are simply labeling this point as out a certain distance M and up a certain distance K. This distance from O to V is out H and up or down 0. So it's on the x-axis, therefore this point is H, comma, 0. And the point U out here then must be this distance here, which is M, plus H. So the x value here is M plus H, so we went out H and then a little bit more, and we got to this point, M plus H, and K. We're up K there and we are up K here. So study that a bit if it doesn't make sense. I think you'll see how that works. But it is a little unusual to be working on a coordinate grid where we don't have numerical values. Now, what we're trying to prove is that this triangle is congruent to this triangle. We have two triangles here, and we want to prove them congruent, and the only information we are given is the coordinate points on the grid. So we're going to have to develop a way of showing these two triangles congruent. Now remember, you have 5 different ways of doing that. Side, angle, side, angle, side, angle, 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 side, 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 and hypotenuse leg. So in this case, we can rule out hypotenuse leg because we don't have any right triangles. Now we have some other possibilities. Let's start with what we could do with the given information. And then you could use one of several different ways here. You could do side, side, side. And the way you would do that is we're going to say UO, or OU, is congruent to itself. Actually, we're not going to use side, side, side because it's the harder or more tedious version. But we are going to use OU is congruent to itself. So I'm going to put point number 2, OU is congruent to OU, and that is reflexive property. Okay, so I'm going to mark that with a single mark, just saying that's congruent to itself. Now, if we think about the distance formula, we could find the distance of this and the distance of this and find them to be congruent, and the distance of this and the distance of this and find them to be congruent. And we would simply apply the letters instead of the numerical values to find distance. There might be a slightly easier way, and that would be if we could find the slope of this line and the slope of this line. That would prove them to be parallel. Then we could establish that this angle is congruent to this angle, and then we apply the distance formula here and here in order to get those two sides congruent. So let's see if we can make it work that way. The slope of a line, of course, is the difference of the y values over the difference of the x values. In this case, it would be k minus k over m plus h minus m. Plus h minus m. K minus k is 0. This cancels this, it's 0 over h, but in fact we don't care what it is underneath, because once we get to the 0 on top, we know that the slope is 0. So over here I'm going to use the distance formula, the slope formula, and I'm going to say that slope m of TU is equal to k minus k over m plus h minus m. And we're going to use as our reason slope formula. we have that well established. We can use that as a reason. And then to simplify that, I can say m of tu is equal to 0. And that's simply simplify. All right, now let's do the same thing for this one. So we're going to say that's, so the slope m of OV is equal to 0 minus 0 over h minus 0. Over h minus 0, and that is slope formula. Okay, and then number 6 is going to be again simplify, and we get m of OV, the slope of line OV, line segment OV, is equal to 0, and that again is simplify. Now, the two slopes are the same. So I can now say, that TU is parallel to OV. Parallel to OV. And the reason for that is going to be definition of parallel. Because if they have the same slope, they're parallel. All right? Now we have, notice what that allows me to do. I can now say angle TUO. So I'm going here, that was 7, this is 8. Angle TUO is congruent to angle, let's see, angle VOU. VOU. So this angle is congruent to this angle, and the reason for that is alternate interior angles. All right, now we have two parts. We need one more part. Let's see if we can find the length of this and the length of this, and then you may see we will be able to use side, angle, side to side, angle, side. All right? So I think I need to, let's see, I'm going to try to raise this a bit. Maybe, let's see, how am I going to do this? Actually, I'm going to, let's see, I'm going to write down the coordinates here. We have mk and m plus uk, m, comma, k, and m plus u, comma, k, for one. And for the other one, I have 0, 0, and h0. 0, 0, and h0. Now, with those written down, I can take this away for a minute, and we can continue our proof over here. Statements and reasons. This is step number 9. And this one, I need to find the distance. So I'm going to say the distance, remember, here, let me write this down just so you remember it, equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so what we need to do then is take, I have the distance of the first one, which was, just a moment here, which was TU, the distance of TU is equal to k, it's the difference of the x's, which is m plus u, m plus h, I'm sorry, this should be an h over here, m plus h. Okay, so now, here, I'm going to move this well over because it's going to be in my way, so let's move that over here so I have enough room here. So, it's the square root of m plus h minus m squared plus, and then the difference of the y values is k minus k squared. All right. This is the distance formula. All right, number 10, we're going to simplify that. And what we end up with is m plus h minus m is just h squared plus 0. Take the square root of h squared, and I get h. So the distance of TU equals h. Now, let's take a look at the other one, which is much easier. The distance of OV is equal to the square root of, in this case, it's h minus 0 squared plus 0 minus 0 squared. This is obviously h squared. The square root of h squared is h. This is distance formula. This is simplify. Now, we're at step number 12, which is the distance of OV is equal to h. Now, look at what we have. The distance of TU is the same as the distance of OV, so I can say in step number 13, TU is congruent to, I should probably say equal to first, is equal to OV because they're both equal to the value h, and that would be a substitution. And then I should say 14, TU is congruent to OV, and that is a definition of congruent. All right? Number 15 then. Now let's go back to what we have. TU to OV. Put that back in here. TU right here is congruent to OV right here. And now we have side, angle, side. And so we can complete our proof by saying triangle OTU is congruent to triangle UVO. And the reason for that is side, angle, side. There you go. We'll continue with this. I may do another one on another lesson, but for now, that gives you the idea of how these coordinate proofs are going to work. Thank you very much.